day. I'm Norman Wildberger. Today we want to start moving towards a bigger picture of linear algebra. We want to look at vectors and matrices in a bigger, novel way, combining our previous understanding of vexels and maxels, which already significantly enlarged the subject. We want to augment that now with our understanding of negative numbers and integers. So we'll get a lot of new exciting directions. And it's really quite fascinating that we can restructure so much of mathematics in this relatively simple way, as we're going to do in the next couple of videos. If you look in a classical linear algebra text, you see statements like this, that here is a vector in R3, or here's a vector in R4. The assumption is that we're so-called working over the real numbers. And we know that that's a little bit of a fairy tale, because if these were really real numbers, they would not look at all like this. They would rather be involving infinite sets of infinite sets, some huge conglomeration that you can't actually write down. So it's very disingenuous to write a statement like this already, because the real number is far from being something as simple-minded as that. But nevertheless, this is the usual story, and the idea is that these kinds of things, say these vectors here, form a three-dimensional linear or vector space, meaning basically that we can add them or scalar multiply them, or maybe combine addition with scalar multiplication. So here's an example of taking a vector, adding a 3 times another vector, and getting another vector. So it's a kind of a closed system with respect to these operations of addition and scalar multiplication. On the other hand, we have, say, R4, which is another space. It's a 4-dimensional space, and it itself also has this sort of closed aspect with respect to addition and scalar multiplication. But generally speaking, these things don't really interact with each other. There's R3 over here, and R4 over here, and R5 over there, R2 down there, and there's this sort of separateness to linear algebra. We are going to be much more all-inclusive. We want to put everything together in one framework so that everything is visible pretty well at the same time. And everything can interact with everything else. So a much richer algebraic structure is what we're interested in. Okay, and for us, well, we're going to be just working over the integers. That's our aim. Okay. In fact, in practice, when you do linear algebra in reality, you always really only work over the integers, rationals, or with floating point decimals. That's just the way the world is. That's the real world. The real world does not use real numbers. But of course, linear algebra is not just about vectors. It's also about matrices. In fact, it's principally about matrices, really. So the classical view of matrices looks something like this. So in a linear algebra textbook, you might see something like this. It's a 2x2 array or matrix. We might use this notation. It belongs to the matrices 2x2 from R. Or over here, we have an example of a 3x2 matrix from R. And again, the R here is quite disingenuous. It's not at all the case that these entries are real numbers, because if they were, then there would be an infinite amount of information encoded there, and there would be some huge infinite hard drive required to specify what's going on there. It's visibly and obviously not what's going on. But students are led to see this kind of thing often enough so that the idea that they're working over the real numbers gradually over many years sinks in. So this sort of residual osmosis of this belief that, oh, we're working over the real numbers when we're doing linear algebra. Well, in real fact, the reality is completely different from that. So in the standard treatment, we look at, say, something like this. It's a 6-dimensional linear space. The space of all 3x2 matrices forms a 6-dimensional linear space, while this 2x2 space of matrices forms a 4-dimensional space, which is also an algebra. So again, we have this idea of sort of separate domains, the 3x2 matrices over here, the 2x2 matrices over here, and so on. Now there is a bit of interaction, but it's very selective. And there's something different that happens for the 3x2 matrices and the 2x2 matrices. The 2x2 matrices are closed under multiplication. So the product of this matrix times this matrix is another 2 by 2 matrix. But we don't have a corresponding product of 3 by 2 matrices. But we could multiply this 3 by 2 matrix by this 2 by 2 matrix if we put them in the right positions. Okay, so again, what we want to do is we want to really expand our view. We want to have a much bigger and broader picture of this whole story. So we want to look at all these matrices all at the same time. Okay, we're creating a framework in which uniformly we're going to look across the entire board and see all the matrices, and they're all potentially able to interact with each other. Okay, it's a much richer and more powerful view than we currently have in linear algebra. It's one of the benefits that one gets by thinking about foundational issues as we're doing here in this channel, and particularly in this playlist. Okay? So one of the only places on planet Earth where we're really taking the foundations of mathematics seriously, and as a result we're able to harvest understanding that's just inaccessible to a lot of other mathematicians. Big advantage in thinking clearly about foundational issues and recognizing the importance, the crucial importance of getting the foundations right. So with matrices, there's a wider choice of possible sizes because it's basically a two-dimensional situation as opposed to the one-dimensional situation for vectors. So we can kind of create a picture like this where we see the various matrix spaces. So here's maybe the space of 1 by 1 matrices, and here's a space of 1 by 2 matrices, and so on. And so there's all these different spaces of matrices currently. And the multiplication of matrices is rather selective. So an m by n matrix can be multiplied by a p times q matrix only if n equals p. So if this number and this number agree, then we are able to multiply matrices of this kind by matrices of this kind, and then we get matrices of the kind m by q. So there's interaction with these matrices classically, but it's a rather selective and limited kind of interaction. So we want to have a bigger picture of this. So the way we're going to enlarge our subject is by taking this 21st century point of view, where we go from vectors to vexels and from matrices to maxels. Now, these are concepts that are built up from a data structure point of view, and they do really depend on having ingested the understandings that we've been developing in this series on data structures. There's a dozen or two videos on data structures of different kinds, sets, multisets, ordered sets, lists. So if you're just coming to this series at this stage, you probably really do want to go back to those videos and watch them and ingest that information. Okay, so a singleton is a list consisting of a single number. In other words, it's a one list. And then a vexel is an M set or multiset of singletons. That's how we define what a vexel is. And a pixel is a two list of numbers, and a maxel is an M set or multiset of pixels. So here very briefly is how we build up what vexels and maxels are. Vexels and maxels are both examples of multisets of a particular kind. A vexel is a multiset whose entries are singletons, while a maxel is a multiset whose entries are pixels. And a singleton is a list of just a single number, while a pixel is a list of two numbers. So this is sort of the one-dimensional version. This is the two-dimensional version. Now, up to now, in our treatment of maxels and vexels, we have previously been working with a framework of natural numbers where we start with 1. Okay, our natural numbers formerly started with 1, 2, 3, and so on. But now we understand that from a multiset point of view, if we're thinking about natural numbers as primitive natural numbers, it's best to start at 0. And so we have to augment our understanding here to stretch it just a little bit further than it used to be, to include not just the natural numbers bigger than or equal to 1, but also 0 as well. So just to make sure we're all on the same page, here is a list of the current conventions or definitions that we're using. So natural numbers means an M set of marks, which includes the empty M set, and that number is called 0. Here is the M set with a single mark. It's the number 1. There's a Hindu Arabic form of it. Here's the M set 2, and so on. So we will be using the Hindu Arabic names for these natural numbers, but we should be aware that it's really these M sets of marks which are the fundamental objects. These things here are just names, convenient names for them. All right, then our singletons. A singleton is a list of natural numbers of size 1. So here are singletons. There's a singleton with the number 0 in it. There's a singleton with the number 1 in it. There's a singleton with the number 2 in it, and so on. So if we actually were officially going to say what this singleton is, we would actually have to replace this 2 with the M set consisting of 2 marks. So technically speaking, that singleton is actually an M set, which contains itself an M set which has 2 marks in it. But we'll stick with that because it's easier for us to understand, although a computer would be quite happy sort of dealing at this more assembly level kind of level. All right, and then a vexil is by definition an M set of singletons. So for example, here is a vexil. It's an M set consisting of singletons. There's a singleton 0, 0, 2, 2, 2, 3. Now this particular vexil can be conveniently represented as either kind of a row vector or as a column vector. But because we're including 0 now, this is a new development that is different from our former treatment of the subject, we have to proceed a little bit differently. Now we have a couple of zeros here. These 2 zeros are represented in a row vector by the number 2 in the 0th spot. And then if we look at how many singleton 1s there aren't any, so we put a 0. We look at how many singleton 2s there's 3 of them. We look at how many singleton 3s there's 1 of them. We look at the number of singleton 4s there's 0 of them. But we don't have to put that 0 there. So this is a representation, this is basically a multiplicity list that describes the M set. But notice that we're introducing something a little bit different. We're introducing this framed first entry. This is now the 0 entry. Formerly we were starting with 1. We would have written something like this if there weren't any 0 singletons. But we do want to allow singleton zeros, and so we want to actually make sure we all understand that this is the spot reserved for 0, the index 0. If we write things vertically, it's the same kind of story. Now our vector is sort of written from top down to bottom, and we have 2, 0, 3, 1, again representing the numbers of 0 singletons, 1 singletons, 2 singletons, and 3 singletons in our M set. So you should think about these things here as being representatives. They are ways of writing down, almost like shortcuts. But this here is actually the real object. Okay? The real object is an M set of singletons, and these vectors are just ways of representing that M set in a sort of convenient shorthand form. Right, so what happens when we go to the two-dimensional situation? We have pixels and maxils instead of singletons and vexils. Well, a pixel is a list of natural numbers of size 2. Here are some examples of pixels. There's a pixel, pixel 0, 0. There's pixel 0, 1. These are lists. You can see that because, first of all, they have square brackets, and there's commas. So the comma is telling us that the order matters. In this little data structure, that's the first element, and that's the second element. And repetitions are allowed. It's a list. So these are all examples of pixels. Pixels from natural numbers. And then a maxil is an M set of pixels, a multiset of pixels. So for example, here is a maxil. And it's a maxil involving pixels 0, 0, 1, 0, 0, 1, 1, 0, and so on. The order doesn't matter. Repetitions are allowed. There's a repetition. There's quite a bit of repetition there. So we can represent this maxil in a more familiar matrix kind of formulation by drawing a two-dimensional picture of it. And this is going to be a little bit of a departure from what we did previously because we have to take into consideration that we now have 0 as a possible index. Which is good. Okay, this is great. This is a great development. Okay, so we have now 0 as a possible index. That means that this top entry here is telling us how many pixels of the kind 0, 0 there are in our maxil. There's just one of these, so that's why we have a 1 there. This is the 0, 1 position, and so how many 0, 1 pixels are there? There's just one of them right there. This is the 1, 0 position, and there are 2 such pixels, so we put a 2 there. This is the 1, 1 position. You can see that there's no 1, 1 pixel, so we put a 0 there. There's no 1, 2. But there are some 1, 3 pixels. There's 1, 2, 3, 4, 5, so we put a 5 there. And this 3 here represents the 3 pixels of the form 3, 2. There's 1, 2, 3 of them, and these are in the position there 0, 1, 2, 3, 0, 1, 2. So this is the 3, 2 position. It might be helpful to sort of label for beginners the position. So that's the 0 position, the 1 position, the 2 position, the 3 position, and correspondingly across the top 0, 1, 2, 3. So what we were doing previously when we were considering maxils just over the natural number starting at 1 is basically we were looking at possibilities that exclude that first top column or row. So basically starting here. So we're expanding that. So now we have a sort of another ribbon on top and a ribbon to the left. So we have a border row and column that correspond to this index 0. And notice that the entries here are not really clearly specified. We could put a 0 there if we wanted to. It wouldn't say anything more. This is just a representation of this thing. So this thing is not really unique. You could put lots of zeros throughout here and then it would look different. But the fundamental multiset that it's encoding is always the same. It's completely uniquely specified. So this is the actual object here. This is a convenient representation for it. All right, so now we're in a position to extend our understanding to integers. So if we're talking about vectors or vexels, why don't we extend to include negative numbers? A vexel is a multiset of singletons. The singletons up till now have just contained natural numbers. So we can extend things by considering singletons of natural numbers as well as singletons of negative numbers. We get a more general object. So this one here has a couple of singletons of -3. There's a -1, a couple of zeros, 4 number 2s, and there's another 0 over there because things are not really ordered. Now this multiset, I remind you, can be expressed sometimes more efficiently by using multiset ideas of arithmetic with multisets. So we can think of it as being 2 times the multiset consisting of the singleton -3 plus the multiset consisting of the singleton -1, 3 times the multiset consisting of the singleton 0 plus 4 times the multiset consisting of the singleton 2. And then if we introduce sort of a more compact notation for this kind of thing. So if we replace this thing with e to the -3, this with e to the -1, e to the 0, e sub 2, then we can express w as a linear combination of these sort of fundamental kind of multisets or maxils. In this case, e sub n is the multiset consisting of the single singleton n, where now n is allowed to be an integer, not just a natural number. So this particular vexel can now be represented in our Fries kind of notation, but we have to extend our view more symmetrically because there are not just a number of zeros, ones, and twos. There's also a certain number of -1s, in fact, one of them, and there's a certain number of -3s, 2 of them. So this row Fries represents this vexel with integer singletons. And note that we put bars here around the 0th entry because this thing is sort of free floating. It goes off indefinitely to the right and to the left. So in order to know where things are, we're going to position the central location very visibly. Right? So this band, that's the 0 label, and that's the 1 index, the 2 index, the -1 index, the -2 index, the -3 index, and so on. And if we wanted to represent it vertically, well, we can just do it this way. There's the column frieze corresponding. We still have this distinguished place that represents the 0 index. And now we have increasing labels going down here and decreasing labels going up here. So now a vector is just a very special case of this more general kind of object, which has both a right-handed and a left-handed aspect. It's now symmetrical. Okay? It's no longer that we're starting on the left and then it's sort of one-sided, building only to the right. Now we have the possibility of having this data structure which is really symmetrical. Okay? That's a very big advantage in thinking about negative numbers as well as natural numbers. We have that symmetry between the two. That's reflected here in the geometry of this frieze. And of course, we can do arithmetic with these two-sided kind of vexels. So for example, here is a vexel and here's another vexel with both positive natural number indices and also negative number indices. There's the 0 spot, there's the 0 spot. If we add them, well, then we're going to add component-wise, but we do so in such a way that the sort of labels correspond. So this 3 here and this 1 will add to give 4. This 0 and 5 gives us 5. This 4 and 2 gives us 6. This emptiness here together with this 1 gives us 1. On the negative side, 1 plus 7 is 8. 0 plus 0 here is 0. And this 2 plus 0 is 2. We see that there's no need for these vectors or vexels to look like they have the same size. That's not an obstruction to being able to do arithmetic with them. Because this is just really shorthand for this, which is more like the real object. So this here is the M set represented by this. We have 2 -3s, a -1, 3 zeros, no 1s, and 4 2s. And over here we have 7 -1s, a single 0, 5 1s, a couple of 2s, and a 3. And when we add them, what we're really doing is we're just doing M-set addition. We're just putting all these singletons together, just putting all of them in and them in the same box or M-set, and then we get this whole collection here. And that's really what we're doing when we're doing this arithmetic here. And of course, then there's the question of how does this all extend to the Maxwell story? We're going to learn about that in our next video next week. Hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.